Today we are going to discuss the heat exchanger designing numerical. First, we will consider a double pipe heat exchanger designing, and then we will discuss about the shell and tube heat exchanger. Now let us consider a double pipe heat exchanger numerical. Now this is a double pipe heat exchanger in which the ethylene glycol and water, they are flowing. Now the ethylene glycol at a flow rate of 1800 kgs per hour is to be cooled from 100 degrees Celsius to 60 degrees Celsius by water available at 15 degrees Celsius. Now here the outlet water temperature, that is not mentioned. However, the maximum temperature to which water can be heated is 42 degrees Celsius. Maximum has been mentioned, but the actual, that is not mentioned. So we can consider the amount of heat exchanged, that is from this 180 degrees Celsius to 60 degrees Celsius, and with this flow rate, that is mcp delta T, I can calculate the Q value, and from there Q for the ethylene glycol, and then the Q for water, that can be calculated. Then ethylene glycol is to be circulated through the tubes. This is mentioned in this case, while the water flows through the annulus of the concentric tube heat exchanger. The ID of the tube, copper tube, while the outside tube is of this T. Then inside diameter of the copper tube, that is 12.5 millimeter. The outside diameter of the copper tube, that is 14.5 millimeter. So the thickness is 1 millimeter. Then the inside diameter of the outer steel tube, that is 22 millimeter. Fouling resistances and metal wall resistances, they are neglected. Suggest a suitable design for concentric tube heat exchanger. So this is the numerical that is mentioned. Now coming to the designing steps of a shell and tube heat exchanger. The first thing is that you have to consider the heat load. You can calculate the Q, which is equal to the mc delta T for hot fluid as well as for cold fluid. Then the fluid physical properties, mu, density, Cp and K thermal conductivity, that is already mentioned. Density, viscosity, specific heat and thermal conductivity, that is already mentioned. You will also require the thermal conductivity of the copper, but in this case the metal wall resistance, that is neglected. That is why there is no need of copper thermal conductivity of the copper. Then the exchanger type, this is our double pipe heat exchanger. Assume the overall heat transfer coefficient. In this numerical, there is no, okay, one by one we will see here. So heat load Q, which is equal to mcp delta T for hot fluid. The ethylene glycol flow rate, that is 1800, that is given, and its temperature, that is to be reduced from 100 degrees Celsius to 60 degrees Celsius. And the Cp value is 2650. So this much watts of the heat load is to be absorbed, this much amount of the heat, that is to be absorbed by a cooling water. So I can calculate the cooling water flow rate considering the maximum temperature of the water, that is 42 degrees Celsius. In the numerical, it is the maximum temperature to which the water can be heated is 42 degrees Celsius. So maximum 42 degrees Celsius and flow rate that can be calculated. So first thing is to delta Tm, that is the log mean temperature difference that is to be calculated. So temperature difference considering the temperature profile diagram for the counter current flow heat exchanger. So your ethylene glycol temperature that reduces from 100 degrees Celsius to 60 degrees Celsius, and for water it is from 15 degrees Celsius to 42 degrees Celsius. So the temperature gradient or temperature difference, that is 142 degrees Celsius, that is taken in this, and delta T2, that is 60 minus 15, that is taken delta T2. So log mean temperature difference that comes as 51.22 degrees Celsius. Then the mass flow rate per unit area of the ethylene glycol. Mass flow rate, that is having the units of kgs meter square second. This is the mass flow rate per unit area. Mass flow rate your kgs per second and per unit area. And this is nothing but U into the rho. U is having the velocity meters per second and density is having the units of kgs per meter cube. Kgs per meter cube. So it's finally unit that comes as kgs meter square second. And this is nothing but the mass flow rate per unit area. And this is needed in your Reynolds number calculation. Du into rho by mu. So G is nothing but U into rho. So in this case, the mass flow rate that is mentioned, that is 1800 kgs per second for the ethylene glycol, converted into seconds, area pi by 4 into d square. Now in this case, di that is to be taken into account. This is di because your ethylene glycol which is flowing through the tubes. So I have to take the inside diameter of the tube, and which is nothing but 12.5 mm. This is the inside diameter of the copper tube, 12.5 mm. From there I can calculate the Reynolds number, which is nothing but du rho by mu, the diameter, inside diameter. So this is the passing through the tubes, Reynolds number passing through the tubes, that is nothing but RET, Reynolds number passing through the tubes, which is equal to the DI into the UT into the rho T passing through the tubes upon mu T. That is all for the fluid which is passing through the tubes. So di is the inside diameter, this is 0.0125. Then G, that is the U into rho, is the capital G passing through the tubes. That is the mass flow rate per unit area. And mu is the viscosity for the ethylene glycol. So Reynolds number, and this is a turbulent region that is observed. The next is the flow is turbulent, so we can use the Dieter-Boltus equation for the calculation of the heat transfer coefficient. So delta Tm that is calculated, this is the shell and tube heat exchanger. It's a simple double pipe heat exchanger. So exchanger, the question of exchanger layout, that will not appear in this case. However, which fluid is there inside the tubes and which fluid is outside the tubes, that is already mentioned in the numerical. Ethylene glycol is passing through the tubes. So exchanger layout, that will not there, and calculation of the HI and HO, that will be there. So HI, that is calculated as 0.023 into RE raised to 0.8 into PR raised to 0.33. So HI into the DI, these are all related to the inside diameter for the tubes. Thermal diameter Di and the thermal conductivity of the ethylene glycol, which is passing through the tubes. And this Reynolds number already calculated. Prandtl number, that is Cp mu upon K. This is the same K. And this HI, that comes as the 3483 watt per meter square Kelvin. Then now we have taken into account the inside tube and the outside tube that is available. This is having the outer diameter of 14.4 millimeter, 14.5 millimeter, and here the inside diameter of the outer pipe, that is 22 millimeter. So this 22 minus 14.5, that is nothing but available this space, annular space. It is called the annular space. So this is your equivalent diameter that will be taken for this remaining section. We don't know the actual, when we want to calculate the velocity, you require the diameter, but for this you cannot have the specific diameter, and for that purpose we calculate or we use the equivalent diameter. And equivalent diameter, that is calculated as the outside diameter inside radius or inside diameter of the outside tube minus the outside diameter of the inside tube. Then the mass flow rate per unit area through the annulus. In this case, the area calculation is of more concern, that is pi by 4 di square minus do square, and the mass flow rate for the water. So your mass flow rate per unit area, that becomes 2186 kgs per meter square second. From there we can calculate the Reynolds number, that is the Reynolds number, which is du rho by mu, and again this is in the turbulent region. So annular flow heat transfer coefficient. Now here we have to use the equation which is suitable for annular flow heat transfer coefficient calculations. The same equation that is used is your Dieters-Boelter's equation, which is 0.023 into Re raised to 0.8 into Pr raised to 0.33. Here also Hd upon K, Nusselt's number 0.023 into Re raised to 0.8 into Pr raised to 0.4. The fluid is getting heated. Here the fluid that is getting cooled. So it is what? The 0.33 and 0.4 that is appearing. Raised to the n, Pr raised to the n, the basic formula was. And here the thermal conductivity of the water 0.614 and the equivalent diameter is 7.5, which we have already calculated here, 7.5 millimeter. So that is all are substituted in the meters and you will get the heat transfer coefficient as 10,000 watts per meter square Kelvin. So after the calculation of the two coefficients, the individual heat transfer coefficient is calculated here as the 3483 and the outside heat transfer coefficient that is calculated as 10,172. So the overall heat transfer coefficient on the outer surface of the tube, UO, we are assuming or we are doing the calculation based on the outside area. That is what we use UO for that purpose. So overall heat transfer coefficient is 1 upon HI dU upon dA plus 1 upon HO. And this gives the 2318 watts per meter square Kelvin is the overall heat transfer coefficient. And from there, we are going to calculate Q, which is equal to UA delta Tm. So area that is calculated as the 0.4464 meter square. And this is not a very large area. That is why we have used the double pipe heat exchanger. And as we are knowing the diameter, the length of the pipe that is calculated as 11.37 meters. So provide this excess 10% length, you will get our actual length of the heat exchanger, that is 12.5 meters is the actual length that is required. So in this numerical, looking to the designing procedure, the data that is mentioned, we have calculated the mass flow rate of the water, the all physical properties that is known. The type of the exchanger is the double pipe exchanger. We have not assumed the value of the U. We have calculated the delta Tm. Then defining the exchanger layout, it is already mentioned that the fluid, hot fluid that will pass through the tubes, then calculation of HI and HO that exist, and then calculate the overall heat transfer coefficient. And one can also calculate the pressure drop in this case. But the fluid velocities or Reynolds number is very low, that is 15,000 and the 19,900, that is around 20,000 is the Reynolds number, not very big values for Reynolds number. So this designing that can be accepted for the double pipe heat exchanger. Then the log mean temperature difference for the co-current flow. This is, we have done it for the counter current flow. It is not mentioned in this numerical that whether it's a co-current flow or a counter current flow. So we are doing it for the counter current flow also calculations. The rest of the calculation related to the heat transfer coefficient, that will be same. However, the log mean temperature difference, that is 43.16, that is for the co-current flow, And for counter current flow, the log mean temperature difference, that was 51.5 51.22 degrees Celsius for counter current flow. And for co-current flow, the log mean temperature difference, that comes as the 43.16 degrees Celsius. So the area required, that increased to the 0.53 meter square, and in the co-current flow. And in the counter current flow, the area required was the 0.4464 meter square. So 0.4464 and 0.53 meter square, that is the difference in the area required. So the similarly, the length of the heat exchanger, that will be also more in case of the co-current flow. So that comes as the 13.5 meter, and with the excess 14.85 meter, that will be 10% excess designing. So 12.5 meter and the 14.84 meter, that means approximately 15 meters length, that will be required. Now the next problem, that is related to the designing of a shell and tube heat exchanger. The horizontal shell and tube heat exchanger is to be designed to condense 3.2 kgs per second of the isobutane at 8.3 kgs per centimeter square. So the vapor's flow rate that is mentioned here, that is 3.2 kgs per second, and the pressure that is also mentioned for the isobutane. Water is available at 25 degrees Celsius and is to be used as the cooling medium. The water is to be used in the other processes until at 37 degrees Celsius. So water inlet temperature and outlet temperature is should be in between 25 to 37 degrees Celsius. The tubes of 15 millimeter ID and 2 millimeter wall thickness are also available. So 15 millimeter ID and 19 millimeter OD, that is mentioned. The tubes are arranged on 25 millimeter square pitch arrangement. This is also mentioned. The tube length also, that is mentioned, that is of the 4 meter. Then the fouling resistance on each side may be assumed to be 0.0004 meter square Kelvin per watt on each side. So two passes on the tube side are to be used. Again, this is also mentioned. Two passes on the tube side are to be used. Then latent heat of condensation, that is mentioned. Then condensation temperature of the isobutane, that is 64 degrees Celsius. What size of the heat exchanger will be able to perform this duty? What size, that is required to be calculated, and for that purpose we have to design the heat exchanger. For a suitable area, calculations are to be done. So the square pitch with the two pass arrangement, that is already mentioned in this numerical, the two passes on the tube side are used. So the value of K and the N, that is mentioned. Again, the assumption of the U, that is already given. This is the isobutane, the organic fluid, and the water. If you will look at the organic water, it is having the overall heat transfer coefficient as 800 to 1500 degrees Celsius. For organic fluids, it is from 100 to 350 watt per meter square Kelvin. And when it's a combination of the organic fluid with the water, the assumption of 400 watt per meter square is a good judgment. Then assume that the condenser is a horizontal unit and the heat transfer coefficient for condensing vapor, the formula that has been mentioned, and this is the same formula for which we have designed or which we have derived in the condensation chapter. So same formula that will be used here. And the physical properties of the isobutane and water, that is your thermal conductivity, heat capacity, viscosity, and the density, they're all mentioned. So this is the numerical. If you will look at this numerical, the data provided is a huge data that is provided for your heat exchanger designing. So one by one designing steps that will be required. We will first consider the Q, heat load, the mass flow rate for the hot fluid, mass flow rate for the cold fluid, mass flow rate that is mentioned for the condensing vapor, that is 3.2 kgs per second. Water flow rate that is not mentioned, so that can be calculated. Its condensation temperature that is mentioned as 64 degrees Celsius, and water temperature is from 25 to 37 degrees Celsius, that is also mentioned. The type of the heat exchanger, shell and tube heat exchanger. Then assume the value of the U, which is already provided in this example, that is the 400 is your assumed value. 400 watts per meter square Kelvin is the assumed value. Then one can calculate the log mean temperature difference, and after that calculation of the area, the exchanger layout, calculation of the individual heat transfer coefficient, and then the calculation of the overall heat transfer coefficient and pressure drop, and finally the optimization that is to be done. So one by one we will look at this numerical. So heat load, this is the condensation numerical. So in this case, the condenser, which is generating 3.2 kgs per second of the isobutane, its mass flow rate that is mentioned, that is kgs per second, into the lambda, which is 275 for the isobutane. So this much amount of the heat that is to be removed. So water flow rate required to take out 882 kilowatts of the heat, you will be required mcp delta t. This is for water, mass flow rate for the water. Q upon cp delta t, q that is 880 kilowatts upon the cp for water 4180, or you can take the 4200 if it is not mentioned. And the temperature gradient for the water, which is the 25 degrees Celsius and the 35 degrees Celsius, 37 degrees Celsius. Maximum temperature of the water, that is 37 degrees Celsius. So I can draw the temperature profile diagram for this purpose. Isobutane, which is at a constant temperature, this is a condensation process. So isobutane, which is at a 64 degrees Celsius, this is the 64 degrees Celsius, the temperature that is there. And for the cooling water, its temperature will increase from 25 to 37 degrees Celsius, 25 to 37 degrees Celsius. This is your 25 degrees Celsius, and for this side it is this 64 degrees Celsius. It is 37 degrees Celsius. So 64 minus 37 and 64 minus 25, that is to be the temperature difference. 64 minus 37 and 64 minus 25. So log mean temperature difference that is calculated as 32.63 degrees Celsius. Then defining the exchanger layout. In this numerical, the tube tube dimensions, that is the diameter, thickness, and the length, all that is mentioned. So have a look. That is the tube of 15 millimeter ID and 2 millimeter wall thickness are available. So ID is mentioned, OD is mentioned, thickness is mentioned, and the length of the tube is 4 meter, that is also mentioned. So this data of diameter, thickness, and the length, that is already provided. Then select the pitch arrangement. a triangular pitch, square pitch, rotated square pitch with a pitch which is 1.25 times the DO or 1.5 times the DO. So in this numerical, this data that is also mentioned. The tubes are arranged on 25 millimeter square pitch. So square pitch arrangement with a 25 millimeter pitch that is already mentioned. In this numerical, that is pitch is directly mentioned. Here it is not defined that it is 1.25 times the DO or 1.5 times the DO. You can do the back calculations for this also, because we are knowing the 19 millimeter as the DO that is available. 19 millimeter, that means 15 plus 4, 2 millimeter thickness. So 19 millimeter is the DO, and if you will multiply by 1.25 into the 19 or 1.5 into the 19, some value that will come around 25 millimeter as the pitch. Then decide the flow of the cold fluid or the hot fluid placement in the inner tube or on the shell side. Also define the number of passes on the tube side and the shell side passes. What is mentioned in this numerical, that is the two passes on the tube side that is mentioned, and generally the condensation that is outside the tubes that is there. So water which is flowing through the tubes will have the two passes on the tube side. Then next is the calculate the outside surface area for one tube, number of tubes, the bundle diameter, the shell diameter, and the baffle spacing. One by one we will see here. So assuming the overall heat transfer coefficient, which is 400 watts per meter square Kelvin as the first estimate, this is already mentioned in this numerical because this is the organic solvent and the water. Then heat transfer area required, which is Q, which is equal to UA delta Tm. Q, that is, we have already calculated Q as 880 kilowatts upon U, which is assumed 400 watts per meter square Kelvin, and log mean temperature difference, which is 32.63. The number of tubes required. Number of tubes required, number of tubes, which is equal to the A upon A0, that is total surface area required for the heat transfer upon the surface area of the individual tube. So the total number of tubes required is the total area upon the area required for the individual tube. The tube area, that is pi dO into L into the N number of tubes, and this is to be equated with this area. So it is assumed that the 5 centimeter tube length will be in the tube sheet and will not be useful for the heat transfer. Therefore, the effective length of the tube that comes as the 3.9 meter. It is already mentioned that the 4 meter tube lengths they are used. So if the 4 meter tube length that is already available, and out of this 4 meter, the tube sheet which is available, and in this tube sheet the thickness of the tube sheet that comes as the 5 centimeter. So the effective length that is remaining as 3.9 meter. Then the cross sectional area of the tube, individual tube, cross sectional area of the individual tube, that is pi by 4 di square. So now coming to the calculation of the heat transfer coefficient. Tube side heat transfer coefficient, cross sectional area of the one tube, which is nothing but ACP, that is pi by 4 into di square. So this is pi by 4 into di square into the n, total number of tubes required, which will be coming as 0.051 meter square. So this is the total cross sectional area in one pass on tube side, which is ACP, which is equal to AC into the NP, number of tubes per pass. So this is already the cross sectional area of all the tubes that is mentioned. Then water velocity through the tubes, which is the flow rate upon area of cross section into the rho. Then therefore use the two passes on the tube side. Here the water velocity that comes as only 0.3456 meters per second. So this water velocity is too less and it will not be able to give the sufficient turbulence, and as a result higher heat transfer coefficients will not be obtained. So we can, to increase the fluid velocity, we can make the more passes. So use two passes on the tube side. However, in this numerical that is already mentioned, the two passes on the tube side are to be used. But why two passes are to be used? It is because of the lower velocity we are using the two passes. If the velocity is low, Reynolds number values are low, then we are using or increasing the more number of passes to create the sufficient turbulence. So two passes on the tube side, so velocity will be doubled. So 0.3456, it becomes 0.69 meters per second. Then after that we have to calculate the velocity of the fluid, then Reynolds number, Prandtl number, that is to be calculated, and in before that the calculate the bundle diameter, calculate the shell diameter, and calculate the baffle spacing. So bundle diameter, that is dB, which is equal to do n upon k raised to 1 upon n. K and n, these values are mentioned. N is the number of tubes. So the bundle diameter that comes as the 0.508 meter. And the shell diameter then, that is 1.1 times the bundle diameter. So 560 mm shell diameter that can be used. Then next is the calculation of the heat transfer coefficient. In this numerical, the different relationship that has been mentioned other than our standard Dieter-Boltus equation. So this is to be used to calculate the HI. So mass flow rate, that is the flow rate upon the cross sectional area into the number of tubes, that is 290 tubes were there total, so half that has been reduced to the 145. Then calculation of the pressure drop, delta P, which is equal to 2F L rho mu square upon di. So friction factor for this 0.079 into re raised to minus 0.25 that can be used. And then the delta P calculations, this friction factor 0.0582, then length and the velocity upon the diameter that is to be used. So pressure drop that will be calculated. Then return losses, as the fluid which is turning, that is there are the two passes on the tube side, the fluid which is moving in the forward direction and there is a second pass. So in this shell cover, the fluid changes its path, and here some losses that can also occur. The losses in the tube because of the friction and the losses in the curvature section, that is half rho u square. So this much losses that can be added. There will be the 5 u bends in the exchanger. So total return losses that will be this much, and so the total losses or total pressure drop through the tubes is 11.11 kilonewton per meter square.